Welcome back to the Deep Dive. Today we're diving straight into, well, what many consider the biggest architectural showdown in AI right now. Transformers versus state space models,
Yeah.
SSMs.
Yeah, these are really the core engines for next-gen AI, aren't they?
Absolutely. And our sources today, specifically this really critical paper from Apple researchers to infinity and beyond, it reveals a pretty massive theoretical vulnerability in SSMs
Yeah.
and also a brilliant solution.
It's definitely an essential topic for anyone tracking model development, especially efficiency. For years, the transformer, the engine behind most LLMs, has really dominated.
Right.
Its main strength is capacity, sure, but that power comes with a significant cost. Computational complexity.
The attention mechanism.
Exactly. That attention part scales quadratically with sequence length, so handling
Yeah.
really long inputs. It just becomes a huge computational headache.
Yeah, a major headache is putting it mildly, isn't it? Quadratic scaling means if you double the input length, you quadruple the compute time, roughly.
Pretty much, yeah.
So that's why when SSMs, like Mamba, for instance, came onto the scene, they seem like such a breakthrough.
They promised efficiency. That's the key thing. Linear scaling in compute time and, crucially, a design that uses a fixed small amount of memory, no matter how long the sequence gets.
Right, that fixed memory was touted as the secret weapon, the path to, like, infinite context.
It absolutely was.
Yeah.
Marketed as the ultimate edge for long context generation. But, and this is the twist, the research we're digging into today exposes a really fascinating paradox here.
Okay.
The very efficiency of SSMs, that fixed memory, comes with an inescapable theoretical chain attached. Left to their own devices, these models simply, well, they cannot actually solve truly long-form generation tasks once the problem gets complex enough. They just hit a hard limit.
Hold on. So they were designed to be the efficient heroes for long stuff, but they fail when the task itself, within that long sequence, demands real complexity. That seems to totally undercut their main advantage.
It does seem that way initially. So, yeah, our mission today is to really analyze rigorously why this theoretical failure point exists, and then explore the very clever way the researchers got around this limit using external tools, interactive ones.
Okay, let's start with that fundamental constraint then, the fixed memory issue.
Right. To really get why they fail, we need to be clear about the model type and the task type that breaks them.
Okay, let's define the model first. The paper talks about generalized state space models, GSSMs.
Exactly.
Wow.
GSSMs. It's a broad category. Includes things like LSTMs, GRUs, and yes, Mamba. The defining feature, the thing that ties them all together, is they operate with a fundamentally fixed amount of internal memory, or state.
Like a brain with a fixed RAM capacity, maybe? No matter how much data flows through, the internal workspace doesn't get bigger.
That's a decent analogy, yeah. And that fixed internal state is really the root cause of the limitation. Standard transformers, on the other hand, they are not GSSMs.
Because their memory grows.
Right. Their key value cache, the memory they use, it actually grows typically linearly with the sequence length. It's less efficient, definitely, but it means they have, theoretically at least, unbounded capacity.
Okay, so the transformer, while maybe slower or more resource-intensive, can kind of buy more working memory as the input gets longer. But Mamba and his cousins can't. So what kind of task pushes this fixed memory past its breaking point?
The paper defines these as long-form generation tasks. Think of problems where the number of possible correct answers just keeps increasing, often exponentially, as the complexity of the problem grows, eventually trending towards infinity.
Can you give a concrete example, something easy to picture?
Sure. Multi-digit addition is a good one. Adding two 100-digit numbers requires keeping track of carries across many positions. Or imagine fixing a bug in a large software project.
Right, where changing one function impacts 10 others.
Exactly. You need to track dependencies, intermediate states, potential ripple effects. The amount of information you need to juggle just explodes as the code base size, the complexity parameter n, increases. The space of correct solutions grows enormously.
And this is where the GSSM hits that theoretical wall you mentioned.
Precisely. This leads us to the core negative finding in the paper. Let's call it the inherent degradation theorem.
Okay.
It essentially proves that for any model with fixed memory, no matter how large you make that fixed memory initially, there will always be some level of task complexity, some n where the sheer number of possible correct outputs or necessary intermediate states exceeds the model's finite storage capacity.
Wow.
The internal state just can't encode enough distinct information to handle the combinatorial explosion of possibilities.
That's quite profound, actually. It implies their efficiency advantage only really holds up for tasks that don't demand true, deep, long-range reasoning or tracking.
Yes.
They physically run out of mental space when the problem gets hard enough.
That's the core insight. And crucially, the researchers demonstrate this failure isn't fixed by just letting the model think harder, using chain of thought, that internal reasoning monologue.
Does help.
Not fundamentally. It still relies on the same fixed internal state. And it also fails even if the model uses what they term single-turn tool use.
Meaning it calls an external tool just once, like asking a calculator for one specific sum.
Exactly. Calling a tool once, getting an answer, and then producing the final output doesn't break the bottleneck. The core limitation remains the fixed internal memory needed to manage the overall task.
Okay, so if the internal memory is the hard limit, and just thinking more or calling a tool once doesn't fix it, the only way out seems to be external memory that isn't limited.
You got it. That brings us to the pivot point of the paper. Interactive tool use.
Interactive, not just single turn.
This is where the research really gets interesting and connects strongly with where AI is going, with agents and frameworks like React.
Right, modders acting in the world using tools.
The core idea is shifting the SSM from just being a prediction engine to being an active agent. An agent that can query tools, read results, write information back to the tool, effectively giving its finite internal brain access to a practically unbounded external scratchpad.
And the key difference you highlighted is the interactivity. Single turn failed, so it must be the back and forth.
That distinction is absolutely critical. The model needs the ability to freely mix internal thoughts, its own reasoning steps, with external commands sent to a tool.
Like read memory address X.
Exactly. Or write 7 to address Y. And then it needs to receive observations back from the tool, like address X contains 4. This multi-step interactive dialogue is what breaks the original limitation.
It sounds like this mechanism cleverly sidesteps the memory problem. If the SSM can't store the whole complex problem state internally,
It doesn't need to.
it just needs to store the current step of the process it's following.
Precisely. The SSM's fixed internal memory isn't burdened with holding the giant, messy state of the whole problem anymore. Instead, it just needs enough capacity to track the state of an algorithm. Where am I in the steps? What do I do next?
And the external tool becomes the unlimited workspace.
The external tool, whether it's a simulated memory tape or a file system or a code execution environment, acts like the tape in a Turing machine. The GSSM tracks the machine's current state, like the instruction pointer and internal register, and the tool provides the effectively infinite tape for reading and writing data.
That Turing machine analogy makes the positive result much clearer. The model just needs to remember, say, I'm on step 4 of long division. The algorithm says read the digit above, now move the pointer left. It's executing a procedure.
You've nailed it. And that leads directly to their length generalization theorem.
Okay, what does that say?
It proves that these interactive tool-using SSMs can achieve perfect length generalization, meaning they can solve problems much larger than they were trained on for pretty much any computationally tractable long-form task.
Provided.
Yeah.
There's a catch.
Provided they're trained correctly, they need to be trained on trajectories that effectively teach them how to execute a valid step-by-step algorithm using the available tools. They learn the process, not just input-output pairs.
The theory is elegant. But did they prove it works in practice? The experiments must be key here.
Absolutely. The experimental results are really striking. Let's look at the arithmetic task first. It's super clean.
Okay.
They set up a simple pointer-based memory tool, like a virtual tape drive. The model could initialize memory, move a pointer left or right, read a token, write a token, basically simulating longhand arithmetic.
And the training data, you mentioned it was small.
Deliberately tiny. They trained Mamba and LSTM models only on examples of 5-digit addition. That's it.
Just 5 digits. And then they tested it on.
Problems up to 1,000-digit addition.
1,000 digits? That's extrapolating, what, 200 times beyond the training data length?
Exactly. And the result. For both Mamba and LSTM using the interactive tool, they achieved 100% accuracy, perfect generalization.
Whoa. Okay, that is the infinity and beyond part, literally. The model didn't memorize addition facts. It learned the algorithm for addition via the tool interactions.
Precisely. It learned the procedure. And here's the kicker, the crucial comparison point.
What happened with transformers?
They trained transformer models, specifically Pythia and Mistral, in the exact same setup. Same tool, same 5-digit training data. They failed. They couldn't extrapolate nearly as well. Performance dropped off significantly on the longer problems.
Really?
The paper suggests this reinforces their core idea. Fixed memory models like Mamba and LSTM, perhaps because of their recurrent nature and fixed state, are inherently better suited to learning and executing these very precise, step-by-step, formalized algorithms when they have that external tool to manage the data. Transformers, relying more on their massive associative memory, seem to struggle with that kind of strict procedural execution, even with the tool.
Fascinating. Okay, so arithmetic is one thing, very structured. What about the coding task? That feels much messier, more realistic for an AI agent.
Agreed. The coding task was designed specifically to test the interactive aspect in a more complex domain. They fine-tuned Mamba 1.4b and a comparable transformer, Pythia 1.4b.
What was the task?
Fixing bugs in Python code bases. They trained them on trajectories collected from simulated coding agents, fixing bugs in code bases containing up to 16 functions. That was the training limit.
And they compared different agent strategies, right? Single turn versus interactive?
Exactly. They had a baseline single-turn agent, diagnose once, suggest, fix, and then 2 variations of interactive agents that could, run the code, see the error, edit a file, run it again, check logs, edit another file, that kind of iterative process.
Okay, and the results?
Yeah.
How did Mamba and Pythia do, especially on bigger problems?
So on the smaller code bases, within the training size, up to 16 functions, the transformer Pythia actually did pretty well. Sometimes better than Mamba. It could probably leverage its larger implicit context capacity.
But the real test is extrapolation, beyond 16 functions.
That's where it got really interesting. On the larger code bases, requiring generalization, Mamba maintains significantly better accuracy than Pythia. But, and this is the key point, only when it was trained to imitate the interactive agents.
So Mamba needed that back and forth tool used to succeed on the harder, longer problems.
Precisely. The Mamba model that was trained on the single-turn agent's trajectories, it failed badly on the complex extrapolated code bases. Its performance cratered.
Which perfectly validates the theory, doesn't it? The inherent degradation theorem strikes again for the single-turn case.
Exactly. Complex bug fixing often requires that iterative loop. Run, check, edit, run again. It inherently needs that unbounded external interaction to track state across multiple files and execution steps. Single-turn access just wasn't enough memory or interaction bandwidth when the complexity scaled up.
What strikes me about this whole thing is the synergy. It's not just that interactive tools solve the SSM memory problem. It seems like SSMs are actually a particularly good fit for this agentic tool-using setup for another reason, too.
Oh, absolutely. You mean because of their efficiency on the input side?
Yeah. All those observations coming back from the tools, long error logs, entire files being read, complex query results, that can be a ton of text, right?
It can be massive amounts of context generated by the tools.
And SSMs, with their linear scaling, are just inherently better at processing that potentially huge influx of information compared to a transformer, where that long context could quickly become prohibitively expensive due to the quadratic attention cost.
That's a great point. The very nature of these multi-turn, tool-heavy interactions generate sequencers that play directly to the strengths of the SSM architecture's efficiency. It handles the interaction flow much more gracefully.
So thinking about the bigger picture then, this architectural fight, transformer versus SSM,
Yeah.
maybe the initial framing was wrong or incomplete. That trade-off of SSM efficiency versus transformer capacity.
It seems it's not an inescapable trade-off, at least not when you look at it from a system perspective. The research shows you can architect around the SSM's inherent memory limitation.
By giving it the right kind of external help.
Exactly. The fixed memory nature isn't a fatal flaw. It's a design characteristic that suggests how it should be integrated into a larger system, specifically one leveraging interactive tools. It suggests the path forward might be less about finding the single best standalone model architecture.
And more about designing the most effective tool-augmented system, pairing the model's strengths with essentially unlimited external capabilities.
I think that's a key takeaway. Competitive advantage might shift towards system design, not just raw model scale or architecture in isolation.
Which brings us to a really provocative final thought for you, the listener, to maybe chew on. If the real-world performance of these models, especially on complex long-form tasks, increasingly depends on how well they operate within these larger tool-using systems, then doesn't that suggest that many of our standard benchmarks today, the ones that evaluate models purely in isolation, might be giving us a skewed picture? Could they be fundamentally misleading about which approaches will actually win out in practice?
That's a really sharp question. What widely accepted AI benchmarks today might become, well, almost irrelevant tomorrow because they simply don't test these critical system-level agentic capabilities that this research highlights.
Something to think about. It definitely challenges how we measure progress.
It really does. Redefining intelligence in this age of interactive, tool-using AI.
Indeed. Well, that's all the time we have for this deep dive. Thanks for joining us as we explored how SSMs can reach infinity and beyond.
Thanks for listening.
We'll see you next time on The Deep Dive.
What if the secret to making AI truly powerful, I mean infinitely powerful, wasn't about building a bigger brain, but just giving it a better notebook? Well, that's the wild idea at the heart of a new paper from Apple, and we are going to dive right in. This question really cuts to the core of a massive debate happening in AI right now. Are we doing the right thing, just throwing more and more money at bigger models, or is there a smarter, more elegant way to get there? This paper basically argues it's all about the tools, a choice between sheer brain power and just being, well, more resourceful. So to really get why this whole notebook idea is such a game changer, we first have to talk about the problem it's trying to solve. Because right now, the way we build almost all major AI models is hitting a gigantic wall. You could call it a computational traffic jam. Okay, so the engine behind pretty much every large language model you've heard of is the transformer. It's amazing at what it does, but it has this one very expensive habit. Its cost to run scales quadratically. Now, what does that mean? It means if you double the length of your input, the work it has to do doesn't just double, it quadruples. And as you can imagine, for really long, complex problems, that just becomes completely unsustainable. This chart just lays out the whole conflict perfectly. On one side, you've got the powerful but super expensive transformer, and on the other, you have this newer architecture called the state space model, or SSM for short. And just look at the difference. Its compute cost is linear, not quadratic. That is a massive, massive gain in efficiency. And get this, its memory is a fixed size. It doesn't matter how long the problem gets. So on paper, SSMs look like they should just blow transformers out of the water. So all right, let's properly meet this challenger. State space models, or SSMs, were basically designed from the ground up to fix this exact scaling nightmare that we see with transformers. The advantages are just so compelling. They're incredibly fast, they're super memory efficient. You've got models like Mamba that are hitting transformer-level performance for just a tiny fraction of the cost. Which of course brings up a really big question. If these things are so great, why isn't the whole world already running on SSMs? Well, it turns out there's a catch. There's a twist in the story. Because the SM's greatest strength, that super efficient fixed-size memory, is also its biggest, most fundamental fatal flaw. The paper has a name for the kinds of problems where this flaw shows up: long-form generation tasks. Basically, just think of any problem where the bigger it gets, the number of possible correct answers just explodes, like adding huge numbers or debugging a massive code base. This is exactly the kind of thing you'd think an efficient model like an SSM would be amazing at. But here's the thing. They're not. They fail. And this isn't just an observation from running some tests. It is a mathematical proof. The paper demonstrates that because of that fixed-size memory, SSMs are provably incapable of solving these tasks once the problem gets more complex than what their internal memory can handle. They literally run out of room to think. And this analogy just hits the nail on the head. Imagine a genius mathematician who can only remember, say, 3 numbers at a time. They can't solve a complex equation, no matter how smart they are. The SSM hits this hard internal limit, so it feels like we're stuck, right? We have to choose between the slow, expensive transformer or the fast but fundamentally limited SSM. But this is where the paper has its big aha moment. What if we could just give that brilliant mathematician a piece of paper and a pencil, a notebook? This is what they call the tool use transformation. The researchers tried a few different ways of doing this. But what they found was that the real magic, the breakthrough, wasn't just giving the model a tool to use one time. No, the key was interactive tool use. This means the model can write something down in its notebook, read what it wrote, think for a bit, and then write something else. It's a continuous loop, just like how you or I would solve a hard problem. And they actually put this to the test in a really practical way. They trained models to fix bugs in software. Now, for small, simple code, the transformer model did okay. But when they moved to huge, complex code bases, the SSM model, Mamba, only succeeded when it was trained to use its tools interactively. It was the perfect real-world proof that their theory was right. And that was only the beginning. Honestly, the results they started getting were just staggering. This simple approach, giving a fast model a notebook, unlocks something called length generalization. It's this almost magical ability for the model to solve problems that are way, way more complex than anything it ever saw during its training. So check this out. They took an SSM model and they trained it on how to do addition, but they only ever showed it examples with 5 digits or less. Then, for the test, they threw it an insane curveball, add 2 numbers that were 1,000 digits long. And the result is, well, it's just unbelievable. The SSM, with its little interactive notebook, got 100% accuracy on those 1,000-digit problems, a perfect score. Meanwhile, the much bigger transformer, even when it was given the same tools, completely fell apart. It just couldn't make the leap from the small training problems to the huge test problems. And you might be thinking, okay, but was that just a fluke with addition? Absolutely not. They saw the same pattern again and again. Multiplication, complex logical reasoning. The tool using SSM could generalize from tiny training examples to massive test problems almost perfectly. The transformer, on the other hand, consistently just hit a brick wall. So, let's step back for a second. What does all of this really mean for the future of AI? Well, it points to a really fundamental shift in how we think about building these things. It's about moving towards smarter systems, not just bigger and bigger models. This research basically presents us with a very clear fork in the road. We can keep going down the current path, building these incredibly expensive transformers, or we can switch to these hyper-efficient SSMs, as long as we rethink what they are. Not as standalone brains, but as the super-fast processing core of a much larger tool-using system. And the big takeaway here is really profound. It shows that a model that might look weaker on its own can totally outperform a stronger one if it's just part of a smarter system. This could mean the future of AI isn't some single, giant, all-knowing brain. Instead, it might be a whole bunch of smaller, super-efficient agents that are constantly interacting with their tools and their environment. And that lightning-fast SSM is really the perfect engine to power that kind of future. Which leaves us with this one final question to think about. What are we really trying to build? A standalone genius? A model so massive that it just knows everything? Or is the better path to build a clever collaborator? An efficient model that just knows how to use its notebook really, really well. The evidence from this paper seems to be pointing pretty clearly to the collaborator.